Hi, everyone. I'm Rachel. I taught a class at UPenn on procedural graphics techniques, and today I want to share with you one of the talks I gave for that class. And the talk covers shape grammars. Shape grammars and formal grammars in general are a really handy technique in procedural generation. And shape grammars in particular are a technique that's used for the generation of buildings and cities. So I want to go over how you can use this technique to generate buildings today. But the reason why I chose this technique is because it really is a very useful general principle, and I hope you'll see why. So to start off, urban environments are a really attractive case for procedural generation. Why? Well, first of all, because there's high demand for complicated 3D assets for cities and buildings in the film and the game industry. And this, of course, costs a lot of artist time. Also, because buildings and cities have lots and lots of repetition. Across different buildings in the same neighborhood, you'll see a lot of basic geometry repeated, a lot of the same footprint used over and over again. You'll see on a single building or across multiple buildings, you'll see structural elements like windows and doors repeated, pillars and columns. You also see the same decorative elements, ledges, corner decorations, tiles, things like that. And of course, textures and materials. So lots of repetition. Of course, this becomes a perfect case for procedural generation. Now, I'll leave the link to these slides up so you can check these examples out later, but the cool aspect of procedural generation is, of course, always that it gives us the power to go infinite. And it's especially cool with procedural buildings and cities. I like this image here, which is definitely just a simple algorithmic approach. Basically, if we can figure out how to combine the basic building blocks in an interesting geometric way, we can produce living architecture in infinite cities as realistic or as fantastic as we want, which is incredibly powerful and very, very, very striking. So let's get right down to it. How do we formalize this technique? Well, before we get down to formalization, let's talk about conceptually what we're going to be doing. So whenever we do procedural generation of assets, I think the fundamental thing is to recognize that we're basically just doing what programmers always do, which is we take a really complicated problem and we identify what the basic components are. So in the case of a building, we might see cubes. Cubes might be the basic building block, or slightly more complicated platonic shapes like are depicted on the left-hand side here. Once we figured out what our basic elements are, we just figure out like in what context they appear. And for instance, on the right-hand side, I might say, all right, a building consists of a bunch of different, basically just fancy cubes, and they can intersect with each other at certain places. And I can add decorations to the top by saying, all right, there's a different class of smaller cubes that can only intersect with the roof parts of my other components. If you've worked with L systems, this is very similar. It's another grammar approach. So once we have our basic building blocks and we've figured out where these repeated elements appear, in what context they appear, we can basically just think like programmers in order to actually go about generating our buildings. So let me give you an example. We have some bag of shapes, and we can basically come up with rules for how we can add on or apply or add on to new shapes from a starting point. So let's say we just start with two different types of blocks in our procedural building toolkit, big blocks and small blocks, as you see on the top here. We can also say that given either of these blocks, we have a rule which can operate on those blocks and add on. For instance, the big block says, I have a rule that tells me to add a small skinny block on top of me and offset slightly. And the small block says I have a rule which adds a big block on, shifted slightly in front of me and to the right. So given different start states, so starting with either a big block or a skinny block, and just repeatedly applying one of these rules, if we just go through many different iterations, applying one rule at each step, we eventually get pretty complicated looking shapes, as you can see on the right-hand side here, despite the fact that we're only using two types of blocks and two very simple rules. So you can imagine how this could very quickly get pretty complicated if we were to use non-trivial rules. All right, now that we have the sort of concept down, now we can talk about formalization. So whenever we work with procedural problems, you can sort of conceive of the procedural problem as having a couple of different steps. First, you need a way of representing the elements that you're generating. So in this case, what I'm going to do is say rather than programming or I need some representation of the geometry I'm working with, I'm going to assign each building block in my building toolkit a symbol. So for instance, I could say that my big block is going to be called A and my little block is going to be called B. The next thing that we need in our procedural generation is a generator, of course, something that operates on the symbolic representation that we've come up with. So a program and a set of functions that operates on those A and B building blocks. And finally, we need a rendering step, which will basically be able to interpret whatever our abstract representation of our system is, the A's and the B's, and turn it into actual geometry. So then we go back from the conceptual blocks into actual geometric blocks. So the interesting thing about shape grammars are that the grammar production process, so the how to apply rules, is intertwined sort of with the rendering instruction. So I just said that we could take blocks and represent them as like A's and B's, and we can do that, but we can also bundle them with extra attributes like position and scale. And every time we apply a rule, we can basically carry over some amount of information, some amount of meta information moving forward. For instance, in the example that we saw here, we have a big block and we said, all right, in shape rule 1, I'm going to take the little block and move it slightly over to the left. And in order to figure out where to put it, we have to actually compute the new position. So let's say the big block is at position 0. 0, 0, 0. The new little block might be at position 0, 1, 1. So that's an attribute that has to be computed. So as we operate on a collection of blocks that are again represented by some symbol like A or B, we have to bear in mind that we need to bundle it with whatever meta information we'll use to eventually render our systems. So this has been a little abstract so far. Let's look at the actual representation of these things. So the basic building blocks in our system are going to be shapes. A shape is the conceptual representation of the data that represents, say, like a block in the example I was just showing you, like one of those individual blocks. A shape has a couple of different attributes. The first one is the symbol, which says, what kind of thing am I? So like in our example previously, we said, all right, we have big blocks, which are A, and little blocks, which are B. So that's what the symbol is. It can be any symbol that represents it. Then next, we might have a type of geometry associated with it. So this could tell me, am I a cube? Am I a sphere? What sort of geometry am I? And finally, we can have a selection of numeric attributes. Numeric attributes can be things like where in the world am I positioned? What's my position? What's my scale? In general, what's my transformation? And you can really include whatever metadata you'd like if it's involved in your grammar production process. Finally, symbols can be terminal or non-terminal. Terminal and non-terminal are used to indicate whether or not your shape can have any more rules applied to it. So how does the production process work? Well, I begin with some collection of shapes. So going back to this first example, the initial configuration in this example is just one block, either a big one or a small one. Next, we pick some shape from our set. We choose a production rule with the current shape S as a predecessor and compute its successor. So what we're doing is we're using a collection of rules, just like the one that we were looking at earlier, which says I have some predecessor, some thing that I'm going to operate on, and I'm going to turn it basically into some other thing. I'm going to turn the predecessor into a successor by applying some function. In this case, we can just call it some f. And we can also have associated with each of our rules some probability. So returning once again to this example, here, the way that we'd represent either of these rules is we'll say we have some block A as the predecessor in our first rule, and the successor is a block, or is an A and a B. And we're adding a new block to our set, which has some new set of rules applied to it. There's no probability attached to each of these because we only have exactly one rule which can apply to our shapes A and B. But if there were multiple rules, then we might apply each rule with some probability. For example, for our big block, I might say I'll actually have two rules. One rule which adds a shape slightly to the left, and one rule that adds the smaller shape slightly to the right. And I can apply each of these with a 50-50 probability. All right, so back to our production process. So we start with some initial configuration of shapes. We pick one, some shape S. We choose a production rule with S as the predecessor, so some rule that can apply to it, and we compute its successor, some S new. And note that S new can be a collection of shapes, not just one. And we add S new to our set, and then we remove the original from our set. And we keep doing that until all the shapes in our set are terminal, meaning none of the shapes that we have remaining can have any more rules applied to them. So this is all pretty abstract. So let's talk about, let's go through a more visual example. Let's say I'm trying to make a building with 4 floors. I might imagine that each of these buildings is, that this building face can be cut into a series of floors, and each of those floors can be divided into a set of windows, and I have 2 window types, A and B. Well, what I can do is come up with a rule which says, well, for every floor in my system, I can replace that abstract floor block with a collection of 4 windows, B, A, B, and I will compute what the numeric attributes of each of those tiles should be based on whatever the numeric attributes of my floor were. So if I have a floor that is of width 10 and height 3, then I know that when I replace that floor with B, A, B windows, they have to sum up to the same size. So each of those window units will be of 3 height, they'll sum to 10, etc. So this is an example of how we can replace one unit with another. Might also be helpful to look at like a larger system. So let's say we want to describe a temple. What I can do is first block this simple building into a couple of abstract component shapes. So for instance, this temple here has 3 main parts. There are the pillars that are in the middle. There's the podium, which is at the bottom, those steps. And there is the capital, which is the roof part, that triangular bit on the top. Now I can further divide these big conceptual blocks into smaller bits. For instance, the middle part, the columns, can be divided into individual columns. So columns, this column section can take a rule which says turn me into actual individual columns, repeated. And each of those columns can be subdivided into a base, a shaft, and a capital there. So each of these parts we can conceive of as being described by some replacement rules. So I can think of an abstract column, but this column actually consists of 3 different parts. And if we split up our conceptual thinking that way, it becomes relatively simple to actually generate pretty complicated structures. Again, this is a pretty simple example, but consisting of just some basic rules. Don't worry about like subdivide or repeat really right now. But this is the sort of basic conceptual framework that we can use to generate quite a lot of complexity. However, something to keep in mind with many, many graphics problems is that adding a lot of geometry willy-nilly can create a lot of intersection problems. For example, let's say I have a rule that says this simple square can grow like a little tower on one side of it. If I have this rule and I apply it like in the bottom image to 2 adjacent squares, I can get this ugly intersection issue. However, there's this nice little hack which we can use, which is all the examples we've been using so far have used an additive strategy, meaning we take some shape and we add on to it. However, we can also use a subtractive strategy, which is we can take a big block and shrink it, make it smaller. Say this big block will become 2 smaller blocks, which fit within the bounds of the original shape. And this is nice because our geometry is only shrinking, therefore we know we'll never have any sort of intersection problems. See, because otherwise, if you were using an additive strategy, you'd have to use some sort of spatial data structure to keep track of what space has already been used, like an octree. Now, when going about trying to generate a procedural building of my own, I definitely used a subtractive strategy because I think it's a little simpler. But again, depending on what you're trying to do, you may find different strategies work better. This is a procedural problem after all, which means there's a lot of creativity and sort of artistic license that goes into the techniques that you use. Now, since we're basically computing what's happening at every step, saying, it's not just as simple as A gets replaced with B. We're saying A gets replaced with B, and B has some set of interesting properties based on whatever the original context was, what the original predecessor was. We can add all sorts of additional logic on top of it. For example, let's say we're generating a city. We can take a noise texture, like depicted at the bottom there, and say, all right, when I'm computing like what I'm going to do at a particular point, I can also say, all right, for whatever point in the world I am, check what is the noise value on my texture, or like let's say my terrain height. You can use any number of things, and say, let's interpret this value as something like population density if I'm trying to generate buildings. So if my value is high, I'll say, then I'll make my building really big. And if my building is small, or if my value is small, then I'll make my building smaller. And this is a nice way of adding conditional attributes and adding more variation into your system. Another tricky thing to think about, and I'm really going to hand wave a little here, is that when you're trying to generate buildings, you also need to keep in mind that unlike with generating wildlife, say plants, things that are supposed to look organic, you do want to mimic some sense of design. Now, don't let me tell you how to live. There are some pretty chaotic looking buildings out there in the world, but if you just apply rules willy-nilly, you're going to end up with chaos. which is why artificial structures have a sense of like human designed organization to them, which makes them trickier than organic structures. We care about things like symmetry or guidelines and things that make our structures look functional, which is something that we have to think about when designing our grammars. So there are a bunch of clever rules that people have come up with in procedural modeling of buildings. For instance, I can come up with some idea of snap lines. I'm going to put some imaginary lines across my buildings at regular intervals, and when I generate different components, say window tiles or anything like that, whenever I fall close to but not on top of one of those lines, I can move things over, like adjust the height of my tile, the width of my tile, in order to snap onto specific lines, which can create some better organization. All right. Now, given all of these things, I want to show you what all of this looks like in action, because I think things have been fairly abstract so far. So this is a procedural building that I built with my good friend Austin, and it uses just the sort of principles that I went over. And from just a series of pretty simple rules, you can get some pretty amazing emergent complexity. I'm no 3D artist. What I did with this 3D castle is I modeled just a couple of different components. I modeled a couple of different wall units like these guys. I modeled just a single roof, which looks like this, and a couple of cylindrical units. Oh, and I have wall units with and without windows. So now, what does this look like? Well, I will show you what the castle generation looks like. So this program, if you haven't interacted with it before, is wonderful. It's Houdini, which is a procedural tool very widely used in the film and effects industries. And what I did is I wrote a bunch of Python scripts, which call upon 3D assets that I modeled in Houdini. So here's a basic castle unit. Looks pretty derpy. And all I have here is I have a really big rectangle footprint, basically. Ignore the roof for now. Let me start subdividing. I have a couple of different rules in my system. One of the basic ones is one that you saw in my slides, which says take a big rectangle and split it in half somewhere, subdivide it somewhere, and randomly shrink the two resulting halves. So that takes us to this iteration. Now, let me apply another rule. Oh, nothing interesting happened there. This just added a little turret on one side. You can see over here. Let's keep subdividing. This splits one of the children that we produced in our first step into two more children, two even smaller pieces of geometry. Let's skip ahead a couple more steps. As you can see, we're recursively subdividing our structures into using just that same rule into more and more pieces. And I also have a little rule that says, shrink me a little bit and add on one of these little tower things. Keep on going. Yet more subdivisions. Skip ahead to like a lot of generations. Houdini is going to spin for a little bit. Aha! Now, the rule examples that I've been giving you have been in 2D, but you don't have to be just limited to 2D. Take a look at this turret in the corner over here. Just like I have a subdivision rule that applies basically on the ground or parallel to the terrain, which says look at my footprint from the top down and split me along some axis. You can also do that along the y-axis. So over here, I've taken a big building and I say cut it in half somewhere along the y-axis, and take whichever or take the half of the building that's on top and replace it with a building that's smaller, it's scaled in, so we have this tower effect. And the roof rule, the reason why it looks so derpy at the earlier iterations is because I just say, all right, take this one roof that I modeled and scale it so that it fits on whatever whatever component building I've made. And using that, you can get this quite intricate looking castle for how simple it is. Let me go back here. This is what a more nicely rendered image looks like for this Houdini castle. All right, so that was a very, very quick overview of how grammars can be used to generate complex structures from a variety of just simple rules. This procedural castle that I made was probably 4 rules, and what I've made for myself is basically a infinite castle generator. I could take this and make a game and have infinite level content in it, and I think that is pretty amazing for how little logic I really had to put into it. It's just when you take even a very simple set of ideas, you add some variety, some bit of randomness to it so that you get different results, and you repeat it over a lot of iterations, you suddenly can get pretty amazing emergent complexity. So I hope that you'll take this talk as a reason to feel inspired to experiment with grammars, not just in urban modeling, but out in all sorts of different procedural projects. So good luck, have fun, and if you're curious about learning more about this topic or anything else, please feel free to check out my class, which has a bunch of open source lectures and starter code for projects and assignments for becoming better versed in a variety of different general procedural techniques. All right, thanks for listening.